In this question, a scientist is investigating a reversible reaction involving hydrogen, nitrogen, and ammonia at 477 Kelvin. So again, we can see we've got that reversible arrow showing the reaction can go both forwards and backwards. We've also been given the K. Remember, K is the equilibrium constant. And that tells us the ratio between the products and reactants at equilibrium. Remember, if K is less than 1, that means that reactants are favored at equilibrium. If K is greater than 1, that means that products are favored at equilibrium. So in this question, we've got K as 0.5. So that means reactants are slightly favored at equilibrium since K is slightly less than 1. We're then also told that at the start of the experiment, the reaction quotient Q is 9.85. Now, the reaction quotient has a similar idea to the equilibrium constant. It's also the ratio between the concentrations of the products and the concentrations of the reactants in a reaction. However, the equilibrium constant is that ratio measured at equilibrium only, whereas the reaction quotient is that ratio measured at any time during the experiment. So Q tells us about what's happening at any given moment, doesn't have to be at equilibrium, whereas K tells us what's happening only at equilibrium. So firstly, if our reaction quotient Q is equal to our equilibrium constant K, that's telling us we're already at equilibrium. Because remember, the equation for reaction quotient and equilibrium constant are the same thing. They're both the ratio of the concentrations of products and reactants. So if our Q value is equal to our K value, that means we're already at equilibrium. If our Q value is less than our K value, in order to get to the K value, we need our Q value to increase. That means our reaction needs to proceed in the forwards direction. However, if Q is greater than K, so the reaction quotient is greater than the equilibrium constant, in order to get to equilibrium, Q is going to have to get smaller until it reaches the equilibrium constant. For Q to get smaller, we need the reaction to proceed backwards. So let's go ahead and apply that to this question here. In this question, K is 0.521 and Q is 9.85. So the Q value is bigger than the K value. So at the start of the experiment, Q is greater than K. What does that tell us about the direction the reaction will proceed? Well, we can look at our table down here. If Q is greater than K, the reaction will proceed in the backwards direction. We know this needs to happen because, again, Q and K, those are both measurements of the ratio of the products and the reactants. If Q is much bigger than K, that means we have too much products and not enough reactants to be at equilibrium. So by proceeding backwards, we're going to get more reactants and less products, which is going to bring down that ratio or fraction until we reach the equilibrium constant K. Let's do one more question of this type. In this question, we have again a reversible reaction involving molecular bromine and elemental bromine at 702 Kelvin. Here's our equation, and again, we've got that reversible reaction arrow shown there, which means it can go either forwards or backwards. We're also given our K value, the equilibrium constant, 1.29 times 10 to the negative 9. So that's a very small value. So that means we're going to have much more reactants than products when we're at equilibrium. We're also told at the start of the experiment, the reaction quotient Q is 5.15 times 10 to the power of negative 12. That value is even smaller than the K value, because to the power of negative 12 is smaller than to the power of negative 9. So what we found here is that our Q value is less than our K value. So we found Q is less than K. Looking at our table down here, when Q is less than K, that means the reaction will proceed in the forwards direction. And again, that makes sense because remember, Q and K are both measurements of the ratio of the concentrations of the products to the reactants. So if Q is much too small, that means we have too much reactants in the denominator of our equation and not enough products in the numerator of our equation. So by proceeding in the forwards direction, we're going to make some more products, which is going to make the numerator of our equation bigger. We're going to use up some of our reactants, making the denominator of our equation smaller, and eventually that's going to lead to our Q value increasing until it's equal to K and we've reached equilibrium. So that's the idea of the reaction quotient Q. The reaction quotient is a snapshot that tells you where you are in the progress of the experiment. If Q is equal to K, that means you've reached equilibrium. If Q is less than K, that means you're not at equilibrium yet. It means your reaction is going to proceed forwards in order to reach equilibrium. If Q is greater than K, again, you're not at equilibrium yet, and your reaction is going to proceed backwards to reach equilibrium.